All right, let's get this show on the road. Hello, students. This is a video review of the Module 1 exam, the first take, long overdue. Okay, simplify these expressions. Oh, and I should make sure my highlighters and my pins are all set up and my PDF interface. Okay, boom. Okay. Oh, let's see. N squared is the largest term in this sum. The 2 goes away, so the solution is big O of n squared. N log n is grows more rapidly than linear 3n, so it is the answer is n log n. The constant 1/4 term goes away. This is Gauss's sum. Well, it's an arithmetic sum, oftentimes called Gauss's sum for no good reason apparently. And we know this equation for it. This is n plus 1 right there, not NH, which would be, is that a chemical? I can't think of it. Might be a molecule. Excuse me. Is it an atom? What am I doing? This isn't chemistry class. This is n times n plus 1 over 2, which simplifies to big O of n squared. But I'm going to have to look that up. NH, is that on the periodic table? Exponential growth is greater than 2 to the n growth is greater than n cubed growth. A constant exponent grows more slowly than a variable exponent. So the answer here is big O of 2n. And the constant does, in fact, the base value does, in fact, matter for those exponential growths. Problem number 2. Find the recurrence relationship for this code that does not much useful. Well, first we notice that our base case is when n is 0, and that's constant time. A return statement. So our base case is t of 0 is 1. There it is. Then what do we do? Well, let's see. This is big O1. This is big O1. These nested for loops from I equals 1 to n, and then again for I equals 1 to n, they have big O1 work done on the inside of them. So this is a n times n nested looping pattern, and it is big O of n squared. So that's for non-recursive. So the work inside of the function for non-recursive calls is big O n squared plus big O1, which simplifies to n squared, and that's this component of the solution. For recursive calls, we go from 1 to 7, and there's just one single line of code in here, and that is a single recursive call. The rest of the code is constant time. So I guess the constant time factor here is n squared plus big O1 plus big O7, because we're doing constant time work 7 times. But the key here is that we're calling compute recursively. We're calling it with 1/3 the size of the input. You could leave these floor bars in on your recurrence statement. Your solution, you weren't marked down for them or for not having them. The key here is that there are 7 recursive calls. That 7 goes here, and the input size is reduced by 1/3, and that is this term right here. Okay. The next 3 questions have to do with this has product with logic. So this is searching an array. I should make sure I can show that. There we go. This is searching an array of integers. Notice there's no stipulations about the integer values. They can be positive, negative, or 0. And an integer b, again, no stipulations. It can be negative, positive, or 0. And this loop is simply finding out if there is sort of a matching pair of elements, if you'd like, such that uh, A times one of the elements is equal to the other. These loops go from 1 to the length of A, both of them. So there's no assumption or requirement that the pattern is sort of forward looking, that I is less than J, or that it's backwards looking, J is less than I. The only requirement is that I cannot be J, and this of course throws lots of fun wrinkles into writing this algorithm for a more efficient asymptotic complexity. But we'll get to that in problem 5. Excuse me. The big O complexity, problem 3, the big O complexity of has product with in terms of in the worst case. So in the worst case, well, let's actually go back to analyzing this algorithm just a little bit more. What we do want to notice is that there is a return true here, which means that, well, the if statement and the returns true in the computation are all big O1. So this is on the face of it, a big O n squared algorithm, 2 nested loops from 1 to n, each of them. But this return true means that on some occasions, we could escape this big O n squared algorithm very quickly. The worst case runtime for this algorithm means that we will be avoiding and never hitting this return true statement. So the type of data provided to this algorithm that would miss this return true statement is, let's see, if none of the elemental pairings meet this requirement, that one of them times b does not equal the other. This is a little mathy symbol that I don't know where I learned it, long time ago. It means for all. So there's this relationship does not hold for all I not equal to j. We don't care about I. We only care about I not equal to j because we are specifically avoiding I not equal to j in the algorithm. So this is either true, there are no matching pairs, or in the worst case, we find the matching pair on the very last comparison. The last term of the array, which means that the outermost for loop has gone through all of its iterations, times b is equal to the last term of, the next to last term, excuse me, of the array, which means the innermost loop has gone through all of its iterations as well. So either of these is a sufficient condition to hit the worst case performance for this algorithm. And you could state these in many different ways. Most of you use sentences because that's what we told you to use. But these are the two relationships that we were looking for in your explanation. Right, and when that happens, when either of these conditions are true, then we go through the full iteration of A for both loops all the time, and the complexity is big O n squared in the worst case. All right. I'm going to erase some of these highlights in case I want to write on the algorithm again for when we talk about the best case. So the best case will be hitting that return true statement as quickly as possible. So we want to hit this return true as soon as possible. So let's think about that. We would like to go through the outermost loop. How many times? How many times should we go through it? How about none? How about let's not go through the entire array A with the outermost loop at all. Let's hit this return true statement on the very first value in A. Now, if we're on the first value in A, and we want to use the same logic for the innermost loop, we don't want J to go from 1 to the length of A at all. We want to hit it on the very first value in the array. But we can't because we have this little niggle here. We got this I not equal to J. So we can't hit the true statement. We can't return true on the first element of A when I equals 1 and J equals 1. We have to wait until J is equal to 2, which means that how much work will we have done in the outermost iteration? We've only done one thing. We haven't iterated through A at all. We've simply started at the first value. So that's just one thing. J has done two things. It has looked at two. It has assumed two different values. One, which was then discounted by the I not equal to J predicate, and then it became 2. Doesn't matter how large A is, you can always have this particular data pattern in it, given that A has at least 2 elements. So the best case analysis, the data pattern is the first value of A is equal to times B is equal to the second value of A, which means, as I have described, the outer loop runs one time, and the inner loop, or the value of I assumes the value once, and J assumes 2 values. This is 1 times 2. That's constant time. So the best case for this algorithm is constant time. Quick reminder, when we're talking about best case analysis for algorithms, you aren't allowed to say the best case is when A is empty, or when A has only 1 element, or 2 elements, or a finite number of elements. You can't discard the importance of expressing your terms for all your solution for all possible sizes of the input. You want to look for data patterns in the input that would allow the algorithm to short circuit or finish more quickly. Okay. Problem 5. This was a tough problem, particularly because of the I not equal to J criteria. So there are 2 ways to solve this problem. You can use there are 2 ideal ways to solve this problem. You can use a data structure. You can use a data structure like a hash table or a set or a map to solve this problem. Or you could sort the array A and take advantage of its ordering to solve this problem. I'm going to present both solutions. To be completely honest, some of the student responses came really close to my solutions, but none of them are my solution. I read everybody's algorithm, figured out if it worked, tried to point out where it didn't work or why it didn't work. But I don't think, I'm absolutely sure no students wrote exactly my algorithm. Or the 2 algorithms I'm going to show as an example. I'm choosing these algorithms not because, they're the optimal algorithms. I think they're going to be the easiest ones for me to explain for how to write a correct algorithm. And that is by far, of course, the most important thing in CS. Write the correct algorithm. Worry about making it faster or optimizing it later. Because, nobody wants to deal with your not correct algorithm. Windows. All right. So there are some important gotchas in this, the problem setup that we need to be aware of. Number 1, B is less than 0 is permitted. Lots of students assume that this could not be the case, and edge cases caught them, caught their algorithm not working correctly. The value, if A has a size of 1 or A has a size of 0, then this algorithm should return false. And if you need to be convinced of that, go back to the original algorithm and look at what happens if A is empty or A has only 1 value. It will definitely return false. It can't do anything else. And then there are some edge cases that we want to be aware of, and these are values or conditions in the data that definitely tripped up um, many solutions by students. The case of b equals 1 and some value in the array equal to 0. And why are these edge cases? Why do these make things tricky? Because when you multiply a times b, when b is equal to 1, you get the value of a back. We know that. 1 is the multiplicative identity. When a is 0, doesn't matter what value b is, you get the same value of a back. And so these are edge cases that we want to make sure these algorithms work for, because this is how we're going to make it correct. So the first example is going to be using a hash table or a map. The nuance here is that as you put things, so the general approach when you're using a hash table to improve a search algorithm is you take the stuff you're looking for, you put it into the hash table, and then you look for it, right? Yeah, this is what a lot of students wrote. The problem, or the nuance here, is that when you put AI times B, or when you just put AI into the hash table, you've now lost where that AI was in the array, and so you can accidentally return true when you're actually finding a matching pair against the very same element, if B is equal to 1 or the value of the array element is 0. The other, right, yeah, I'll leave it at that. The way to avoid this, straightforward way to avoid this, is to build your hash table or your set as you traverse through the array A. Do all your inspections first so that if you find a match, you know you can't be matching against the element that you're on because you haven't put the element that you're on in the set yet. Ooh, I love this idea. So we create an empty set. Doesn't matter if it's you call it a hash table or a binary search tree based set. Then for every element in A, we ask, is B times A inside of our set? And if it is, then we have found a match. And it can't be a match against the value of A we are sitting on right now in the array because it's not in the set yet. Its value might be in the set because some other element in the array has the same value. Some previous element in the array has the same value. But our element is not. It has not been added to the set yet. And if it satisfies this condition, B times A is in the set. If B is equal to 1, we might find our own value. Otherwise, we'll find another value, which is the match. And once we do that, we can return, boom, we're out of here. Now, the other nuance of using the set like this and building it as we go is that all the elements in the set that were before us in the array A don't have an opportunity to check if I, or the element that we are on right now, is its matching pair. So we need to do that check for them. We not only need to check to see if a previous element in the array is equal to B times ourselves, we need to make sure that a previous element in the array times B is not equal to us. So we do that next. If some previous element in the array times B is equal to us, then A mod B must be equal to 0. But we can't compute A mod B equals 0 unless we know that B is not the value 0. So we make these two checks, and then we check, and then once these have been satisfied, we know that A divided by B, so this is us divided by the value B, this will be the value of the element in the array that we are the pair of, the element in the set that we are the pair of. It's also in the array, yes, but key is that it's in the set. Um, and so we ask to see if it's in the set, and if it is, then we can return true. Yay, we're out of here. If both of these fail, then we simply add ourselves to the set and we carry on. If we go through the entire array and we've never returned true, then when we're done, there are no matching pair or pairs of elements in the array, non-reflective, not when you consider a pair against itself, that hold to this criteria: AI times B equals to AJ. Does this algorithm work for the edge cases? If A is 0 or A is, if the size of A, and these are cardinality bars, not absolute value. Cardinality means number of, or the size of a set. Is the array empty, or does it have only one element? Well, if the array is empty or has only one element, yeah, if it has only, if it's empty, we won't even traverse this and we return true. If it has only one element, then both of these are going to be false, because the first iteration through the array, S is empty, will finish by adding that one element to S, but then the loop finishes and we return false. Okay, that's good. I like that. Hit those edge cases. Boom, boom, boom. If B is 1 or B is 0, well, let's see. If B is 1 and B is 0, recall that the niggle here is that when those two, when B equals 1 or the value of A that we are on is 0, that can create problems, because we might find our matching pair that is actually ourselves. But this cannot happen in this algorithm because we don't put ourselves into the set until we've already looked for matching pairs. So the edge case for B is 1 or 0 is inside of A is handled by the structure of our algorithm. And then let's see, if B equals 0, is that an edge case in this particular algorithm? Let me think about this. Oh, right, yeah, it is, because we're going to be doing this A divided by B thing, but we only do that if the value of B is 0. The analysis of this algorithm: this algorithm, if S is represented in a binary search tree, then n times in the algorithm, we search the tree or we add to the tree. We could actually do it 3 times for each loop. Each one of those is a log in operation. This is assuming that it's a balanced binary search tree, but that assumption would be fine with us. Right, so I guess it initially is big O of 3n log n, but that simplifies to big O of n log n. If S is a hash table, then searching the hash table is big O1, inserting into the hash table is big O1, so it's n times 3 work inside the loop, which simplifies to big O of n. Isn't this a fun problem? I love this problem. Maybe I didn't when I was grading it, but it does have its pluses. Right. A solution that instead of using a hash table or a set, sorts the array A. The key here is we need to be careful to not return true when we look for AI times B, because if B is 1, we will definitely find that term inside the array. It is us. Or if AI is 0, we'll definitely find that term in the array, because yeah, again, it is us, and AI times B won't change the value that we're looking for. So the very first step in this approach is to sort A. I chose merge sort because who wouldn't? Um, and that's an in-log in operation. And then we're going to do a loop, a counting, an indexed loop through A. It's going to be important for us to know the location we are at inside of A as we go through this algorithm. So I'm not using the type of loop I used in the previous example where I just said every A inside of the array. I'm going to keep track of where I am in the array because it's going to be important. So I do a search. I use binary search. This is a log in operation, and because A is now sorted, and I am searching explicitly for B times AI. If I found it, if I found the value B times AI and B does not equal to 1 and AI does not equal to 1, then I can return true. Why do I need the criteria for B not equal to 1 and AI not equal to 1? Because if B equals 1 or AI is equal to 0, I think I just said AI equals 1, I meant AI equals 0. If that's the case, then searching for B times AI is the same as searching for AI. And we will find AI because that's us and we know that we're in the list. We're in the array. So if we found a match and it is not us, then we return true. Otherwise, well, what do we do? So if we do, oh my gosh, I wrote a bug inside my own example code. I'm so happy somebody caught me, maybe? Oh, lordy. Oh, now I'm drawing in white and erasing. Okay, you're going to just have to bear with me. Oh, I know what I want to do. Huh? Will that work? Oh, great. Screen. Can't believe I did this. Found and I should be consistent. And so why does my pencil not? Why am I drawing a rectangle? Jesus. Oh my, I'm so sad. There we. All right. I need a found and. Yeah. Oh, wait a minute. I'm an idiot. I'm so sorry, people. I'm going to erase this. Just let that hang. All right. A little hanging chat of my video review. Okay. I'm not going to start over, but I am going to start on the last if predicate that we went through. If we found the term and it could not possibly be us, then we return true. But now we still have to handle the case where B is equal to 1 or AI is equal to 0. Or there is some element in the array that is equal to 0. Those are perfectly valid inputs for the algorithm. We should return true if there are two values of AI in the array and B is equal to 1, or if the current value we're on, AI, is equal to 0. If there are two values of 0, or two values of the array, or two values of the element in the array, and B is equal to 1, we should return true. So we have to check to see if there are two values of myself, if you will, of AI in the array, which you might think is, well, that's going to be a pain because that's a big O in search of the array. And to which I say, nay, 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 because this array is sorted now. So if there is another value, it must be the next value in line. So as long as we are not at the end of the array, we check to see if AI equals AI plus 1. And if it is, and b equals 1 or ai equals 0, then we've met the criteria for the return value of true, and we can return true. Got completely flabbergasted there. Thought I made a mistake, and then I didn't, and then, well, yeah, then the wheels kind of came off. So my apologies. Okay. If we go all the way through this array and we never return true, then we can return false. Let's check the edge cases. If the array is empty or the array has only one element, well, if it's empty, we won't iterate, we'll return false. If the array has only one element, then if we do find a term, then it means that b must be 1 or the value of a must be 0. The only value in the array must be 0, in which case we won't hit this return true. We won't hit this one. But we will check this, but I will be, oh, there is a mistake in my code. This should not be I less than or equal to n. This should be just I less than n. Always one, Hellman. So if we're not at the end of the loop, end of the array, then we can check the next value. But this will not be true in the case of a containing just one element, and so we have to return false. If b is 1 or b equals 0, we handle these cases appropriately inside the for loop. I think I've gone through that logic already. And if if b equals 0, we don't divide by b at all. We don't divide by b at all in this algorithm, so that's not, in fact, an edge case. The complexity for this algorithm, let's see. Merge sort is n log n. Right, yes, n log n. Searching is log n, and all the rest of this mumbo-jumbo inside of the for loop is constant time. So we have a sort loop. We go through the loop n times, do log n work on each one for one search. And that turns out to be big O of n log n. You could, of course, after you've sorted the loop, you could put this entire for loop inside of logic that checks the value of b and a first, but I don't think that's necessarily beneficial. The last question, I believe, is problem 6. Is this the last question? I don't know. We're just going to keep on grinding. Problem 6, resolve the recurrence relationship. Okay, let's see. So the unifying theorem, well, let's not do this in red, Hellman. We've had enough of that today. Oh, stop choosing it. Let's do orange. Okay. The unifying method, we compare the value b to the value of a in the recurrence relationship formula. So the base of the logarithm is the factor by which we're dividing the input size by for each recursive call. The argument of the logarithm is the number of recursive calls in the algorithm. Log base 3 of 2 is certainly less than 1, which is also less than 2. This, I hope, goes without saying. And 2 is the value of d inside of the recurrence relationship. That's the polynomial power of n for the constant time work. And the unifying theorem says this should be theta of n squared. If you use the substitution method, I don't think I saw anybody do a substitution from the root of the tree down to the base case. The only ones I saw were from the base case up. So if to do the substitution from the base case, we start at t equals 1. The next value we want to choose is t equals 3 because that makes 3 divided by 3 easy, and we know the answer of big T of 3 over 3. That's big T of 1. And we're going to plug that in, so we get 2 times 1 plus 3 squared, which is 9, which is 2 plus 9, or 11. Then we go to T of 9. T of 9 over 3 is T of 3, which is 11. So we get 2 times 11 plus 81, which is 103. We do this very same process for T of 27, and I took it out to T of 81, and you certainly could have as well, because you all had calculators. And what do I notice here? What do I notice? So all these summations, 2 plus 9, 22 plus 81, 200 plus something close to 800, 1800 to 6,000. All these terms are about a quarter or a third of n squared. This is about a quarter or a third. This is about a quarter or a third. This is about a quarter of a third. This is about a quarter of a third, you know, give or take. So the 2 times t of n over 3 term is always about 1/3 of the non-recursive work that is done. So I can say t of n is about big O of n squared over 3 plus n squared, and this simplifies to just big O of n squared. And then our favorite, the tree method. Notice that the work done in this recurrence relationship is not just n, it is n squared. So we need to keep track in our tree of 2 different values, the input size, n, and the work done at that node, which is n squared. In the first generation, we'll have the input size of n over 3. That comes from this term. And the work done is not n squared over 3. It is this entire n over 3 squared. It's n squared over 9. The next generation down will have an input size of n over 9, which is n over 3 divided by 3. And its work done will be n squared over 81. I have created the canonical table over here, labeling my levels from I equals 0, 1, and 2. Number of nodes is, what is this? Well, this is always a power of 2. We add 2 nodes. Yeah, we don't add 2 nodes. The number of nodes increases by a factor of 2 for each generation down. The work done per node at the root is n squared. At the first generation down is n squared over 9. At the third generation down, n squared over 81. We can generalize this for the ith layer. It is n over 3i squared. So this is the size of the input at a particular layer. And then the work done is the input squared. How many nodes do we have at that layer? That's 2 to the i, because each node in a layer is generating 2 children for the next layer down. And we can simplify that into what? 2i times n squared over 3 squared. I'm just going to flip-flop the 2 and the I and the exponents here. And this is a nice, this is a general term for the amount of work done per layer. So now we need to add up all the layers, and we do that with summation notation, of course. And the critical question is, what is the height of the tree? How many layers are there? I'm getting a little tired of orange. I'm going to switch to green now. What is the height? Well, it's 1 plus log base 3 of n. It's how many times can you divide n, assuming that it's some power of 3. How many times can you divide it until you get to the base case of 1, which will be the last layer of the tree. And that is log base 3 of n. And this plus 1 comes, and we need this plus 1. We can check to make sure we're right. If n equals 3, then our tree looks like this. N equals 3 there, n equals 1, n equals 1. Those are the base cases. And so the height is, of course, 2. So it's 1 plus log base 3 of 3. And that works out. So we need to add up this general term for the work done per layer by as many layers as there are, and we begin at I equals 0. So we have I equals 0 to log base 3 of n. That 1, yes, is accounted for by the I equals 0 term. We are adding up n squared times 2 over 3 squared to the I. That's n squared times 2 over 9 to the I. We can take the n squared out because it's independent of I. This is just algebra. This right here is less than the geometric sum to infinity of 2 over n to the I. This is the convergent geometric sum with the base less than 1. And so we know that its sum out to infinity is actually this finite value. And right, we simplify that to 9 over 9 n squared over 7, and that simplifies to big O of n squared. Well, there we go. We're up to module 2, so I'm going to stop this video now. Have a good afternoon, everyone. Oh, I'm slouching in my chair. Sorry about that. Turn the video off.